Hi friends, let's solve this problem based on basic MOSFET circuits. So here it is asking to calculate V1, V2 and V3 for two different conditions, that is W by W over L ratios of two transistors are equal, that is 20, and in second case that is something different. So let's start with the part A now. So here it is, simply W over L ratios are same for the both the transistors, and both the transistors having similar parameters, and both the transistors gates are connected to ground and sources connected together, and same VDD supplies, same drain resistance, everything is same. So we can expect the drain currents ID1 equals to ID2 is exactly half of the 200 microamperes, that is 100 microamperes we can expect simply. So V1 and V2 part is very easy actually. So V1 simply we can write 2.5 volts minus 20 kilo ohm multiplied with 100 microamperes. So it is 2.5 minus 20 10 to the power of 3 multiplied with 100 microamperes. So it is a 0.5 volts. So, and similarly V1 and V2 both are equal to 0.5. So this is actually very easy one. So let's look at V3 now. So let's write a current equation for any one of the transistor. So mu1 times W over L multiplied with, let's write for transistor 1, that is VGS1 minus VT whole square is equals to some 100 microamperes. So let's substitute all the values, and let's see. Kn dash is given 125 microamperes per volt square. So it is 125 microamperes per volt square. This is a 20, and this is VGS1 minus VT also given, that is 0.7 whole square is equals 100 microamperes. So now let's use a calculator. Let's use a calculator to calculate how much this can be. So this is 100 microamperes divided by 62.5 10 to the power of minus 6. So it is under root of 1.6 over 20. So it is 0.2828 for the VGS1 minus 0.7. So let's take VGS1, this is 0.9828 volts, but VG minus VS for transistor 1 I'm telling 0.9828 volt, but VG is clearly 0 volt. So VS is, because VG already grounded, so VS is minus 0.982 volts. So this is a part 1 actually. So let's go for part B now. So in part B everything is same, but the width to length ratios are changing here for transistor Q1 and transistor Q2. So here we can expect for part B, we can expect that ID1 is ID1 is 1.5 times of ID2. That is drain current of transistor Q1 is 1.5 times of drain current of transistor Q2, because every parameter is same but only the width to length ratio is changing here. So we can comfortably assume this one, ID1 is equals to ID 1.5 times of ID2. So here let's take ID1 plus ID2 is 200 microamperes, but ID1 is 1.5 times of ID2, so ID2 plus ID2 here is equals to 200 microamperes. So ID2 is 200 over 2.5 microamperes. So this is how much? This is 80 microamperes, and ID1 is obviously 200 minus 80, that is 120 microamperes. So with this we can simply tell what is V1 and V2. V1 is 2.5 minus 20k ID1. ID1 is 120 microamperes. So let's use a calculator for this. How much this can be? This is a 120 10 to the power of minus 6. So it is 0.1 volt. 0.1 volts. Similarly, we can write V2 also 2.5 minus 20 kilo ohm multiplied with some 80 microamperes. So let's use a calci for this also. So it is a 0.9 volts. So now here we need to calculate what is a V3 here. So let's take what is V3 here. So let's write a current equation for transistor Q1, that is ID1. We also know that that is 120 microamperes is equals to half mu n C naught x is 125 10 to the power of minus 6. W over L ratio is a 20 for transistor Q1, and VGS1 minus VT 0.7 whole square. So it is clearly now let's use a calci for this. 120 multiplied 2, 125 multiplied 20. So it is VGS1 minus 0.7 whole square is 0.096. So 0.096. So it is a VGS1 minus 0.7 is 0.3098 volts. So VGS1 is clearly 0.7 plus 0.3098. So this is 1.0098 volts. So clearly VG is 0. So VS1 is minus 1.0098 volts. This is also equals to the voltage of V3. So in this way we can solve MOSFET problems at DC voltages. Thank you for watching. Please subscribe my channel.